Alright, so what we want to look at now is kind of shifting gears from sketching curves to now optimizing things. And what we're talking about optimizing is we're talking about having the best solution. Now, what we mean by best is going to vary depending on the situation. We might want the maximum of something, or we might want the minimum of something. But best is going to be determined by the situation. All right, so here's an example of a situation. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume, okay? So you see here a picture of the box. Now you won't always be given a picture, but you're going to want to draw a picture, okay? Now this picture is a little bit deceiving because they forgot one of our sides. There's a back side to this as well, okay, back here. And it just has an open top. Okay. Now, you can see here there are some examples. Some examples of boxes that have a surface area of 108 square inches. We could have it be 3 by 3 on the bottom. Okay, so it's 9 square inches on the bottom. So that makes it a total of 12 square inches around the bottom, and then it's 8 1/4 inches tall. So 12 times 8 1/4 is going to be 99 square inches plus the 12 on the bottom, or I'm sorry, the 9 on the bottom. That's 108 square inches. Okay, or we could have one that's 8 by 8 on the bottom and only 1 1/8 on the top. Okay, so the bottom of that would be 64 square inches. The perimeter is 64, and 64 times 1 and, oh, that's 1 3/8. So 64 plus the perimeter is 32 times 1 3/8. Okay, so that's going to be 56. 56 plus 64 is 108. Okay, or you have this one, it's 5 by 5 by 4 3/20. Alright, so the bottom's going to be 25, the perimeter of the bottom's 20, so it's the perimeter of the base times the height, 4 3/20. That's going to be 83. 83 plus 25 is 108. And you guys get the idea. There's a lot of different options for how the manufacturer could build this box. However, the reason they want 108 square inches for the surface area might be that that amount of material is going to be the best for their costs. You know, the bigger the surface area of their box, you know, the more it's going to cost because you need more material to build the box. All right, so they're limiting it to 108 square inches, but they want to be able to fit as much as possible in it. So we want to maximize the volume. And as we are looking at optimization, that statement right there is the statement that you want to look for in every one of these problems. What are we trying to maximize or minimize? Okay, in this case, the best situation is the situation that gives us the greatest volume, the maximum volume. The reason why that's so important is because not only is that going to tell us what we're looking for, but also that's going to tell us typically what formula we're going to be using. The volume of a box. Okay, so the volume of this box is x times h. Okay? Now, this is where it can be a little bit tricky. Because notice, this is not like a related rates problem where we're given different rates of change. Okay? We can't leave that H in there. We need to get the volume in terms of just X. Now, does anyone have an idea of how we could express H in terms of X?
Do you like a sine function? Sine and cosine?
How would you do that?
I don't know, I'm just spitballing.
Okay. That's a thought. Winnie?
Because we know the surface area, so like it consisted by 5 sides, and then we know it's a square at the bottom. So we can use like saying 109 minus x squared, then minus not minus, and then divided by 4, sorry, divided by 4, and then divided by 4x, yeah.
Divided by 4x. Let's see what you're using the surface area, right?
Yeah.
Okay, so let's look at that. Surface area equals the area of the base, which is x squared, plus the perimeter of the base, which the perimeter of the base is 4x times the height, right? Now, like she said, we know that the surface area is 108, so if I plug in 108 for the surface area, and I solve for h, that's absolutely correct. I'm going to subtract the x squared and then divide it all by 4x. Okay? So, yeah, really good. So now, notice I can write my volume as a function of x. Notice before it was just a formula. Now I'm actually writing it as a function of x because I'm going to substitute in what I just found, or what we just found, 108 minus x squared over 4x. And now I see my volume. And let's go ahead and distribute in the x squared. The x squared is going to cancel with the x in the denominator. So now I'm just distributing in an x. So that's going to be 108x minus x cubed over 4. That's going to be our volume as a function of the length of the base. Okay? Everyone with me there? Now, why did we bother doing this?
So let's get it all in terms of x, because then once you find x, then you go play with it, rather than writing it 2 variables.
Okay.
And like, I feel like maybe if you take the derivative and find a max point, then that's where you find the best volume.
Okay, yeah, we're trying to maximize the volume. So if we can get a function for the volume, we can find a max point. Now you can see here, this is going to be a cubic function. The x cubed is negative, so it's going to look something like this. All right? Now there is a range of possibilities. We know x cannot be less than what?
0.
0. Okay? We know x can't be less than 0. So
be higher than 108.
It's got to be greater than 0. It can't be less. It's got to be less than
108.
if h were 0. If h were 0, that means x would be the square root of 108, right? So we know x has to be less than the square root of 108. That gives us a range of possibilities.
I just get that.
Because if h were 0, then the base would just be this flat thing with an area of 108 square inches, right?
No.
So each side would be the square root of 108.
Okay.
Okay? Now, you can't, that's no longer a box because there's no height to it at all. So I know x has to be smaller than that value in order to have any height at all. Okay? So now I have this range for x, and what's going to happen here is I'm going to have a cubic function. It actually does go through, it goes through the origin. Oh wait, it's actually going to go like this. Okay? My zeros are going to be negative square root of 108, positive square root of 108, and 0. Okay? Now you don't have to find those in this case, but I'm just showing you this is why what Evan said is absolutely correct. If we can find where the derivative equals 0, that's going to give us the max point, which will give us our max volume. Okay? So, let's go ahead and find v prime of x. Alright? This one's kind of nice. It's just, I can just leave it over 4 because that's a constant multiple. Alright? So it's going to be 108 minus 3x squared. Okay? And now I just, I'm going to set that equal to 0 to find my max point. So if I multiply by 4, I just have 108 minus 3x squared equals 0. That means 3x squared has to equal 108. So now I divide by 3. And that's 36, right? Okay. And that means x has to be plus or minus 3.
No, this is plus or minus 6.
Yeah, 6. Sorry. Plus or minus 6. Which actually, if you look at this, notice we have a max point and we have a min point. Again, this is where our knowledge of precalculus and the functions that we're dealing with is helpful. This is going to be negative 6 something, but I know x can't be negative, so I don't care about that point. I know x has to equal 6. Alright, so there's 6, and that's the point 6. We weren't asked for what the volume would be, but we might as well find it. 6 times 108 minus 6 cubed. 6 cubed is 218. And 6 times 108 is going to be 648. So 648 minus 218 is going to be 330. Divided by 4 is 330 divided by 4 is going to be 82 and a half. Did I do that right?
82 and a half times 2 is 164.
Now, one thing to be careful about here, make sure you answer the question. What were we asked to find?
The maximum volume. The dimensions that'll produce the maximum
The dimensions. What dimensions? What do we mean by dimensions?
X and H.
X and H, okay? So X is 6 inches, and now we need to find H. Well, H we already know is 108 minus x squared over 4x.
72 over 36.
So 108 minus 36 is 72 divided by 24, 3 inches. Okay? So our dimensions are 6 by 6 by 3. Okay?
6.
Dimensions 6 inches by 6 inches by 3 inches. Okay? Now, one thing to be careful about. Notice we found that range of reasonable possibilities or realistic possibilities. X had to be between 0 and 108 or square root of 108. You need to make sure that you check the endpoints of that interval. Now in this case, we know the endpoints are not possible, and because of the shape of this graph, we know that this is going to be the absolute maximum. But here's where relative max and absolute max can come into play. Not in this example, but it can come into play, all right? So, that's one example of how we can optimize a situation. We're finding the best solution, which is the one that gives us the greatest volume under a certain set of circumstances. Let's double check that volume here. X squared is 36 times 3. That would be 108 for the volume. So actually the volume isn't 82.5, it's 108. So the maximum volume is 108 cubic inches. Now, you don't have to find that if they don't ask for it. It can't hurt, but yeah, thanks for catching that. Okay? That's what I get for doing too much in my head. All right, so let's look overall at some guidelines here, okay? Here's some guidelines. You're not always going to be given a diagram or a picture to go along with it, so identify what you are given. And guys, I'm not just saying identify it mentally, but really take the time to write it out. It's worth it, okay? Write down x equals this, or h equals this, or in this case, s, the surface area, equals 108. That way you're not having to go back to the paragraph and try to find that information again. I'd also recommend, as you're writing it down, write down the proper units of measure, too. Okay? Write a primary equation for the quantity that is to be maximized or minimized. That's where we put the volume equaled x squared times h. Okay? Reduce the primary equation to one having a single independent variable. That's where we had to represent h in terms of x. So we could actually write our volume as a function of just x, not x and h. Okay? Now we may have to, like in this case, we use that surface area formula to be able to figure out how to relate them. So we may need a secondary formula here. Okay? Then, fourthly, determine the feasible domain of the primary equation. In other words, feasible means realistic or logical or possible. So in our case, we knew x couldn't be negative, and we knew the surface area couldn't be bigger than a certain thing, and so the height couldn't be negative. So we were able to come up with that range from 0 to the square root of 108. That x had to fall inside. And then using your calculus, getting the derivative, and finding the max or min point, you're able to then find the optimal solution. Okay? So that's kind of a general guideline for solving these. All right, so let's look at one other example here. This one's a little bit different. We're trying to find the point that is closest to another point. The point that is closest to another point. So let me make a sketch of this first of all. Y equals 4 minus x squared. I know this is our parent function x squared, shifted up 4, but then flipped horizontally, reflected down. So it's up 1, 2, 3, 4, but it's going downward like this. Okay? Now, I can see the zeros here. Where are the zeros of this function? Just
There's two of them.
there's 2 of them. Where does this equal 0?
-2 and 2.
Yeah, -2 and 2. Okay. Now, do we have to know that? No, but can't hurt. All right. So we want it to be closest to the point 0, 2. Now, how do I measure distance from a point to something else?
Straight line.
Okay, the distance formula, it's got to be a straight line between them. The distance formula, okay? Now let's think about our distance formula. I'm gonna come up with this point P that's on the function. Here's the point 0, 2. And I'm gonna make this point P x, and then what's the y coordinate of this gonna be?
Oh wait.
3.
Maybe.
That point, some y point.
Some y. So what's y in this case? If it's on the parabola,
4 minus x squared.
there we go. If it's on the parabola, I know that y has to be 4 minus x squared. That right there is the key to this whole problem. When you are looking at closest, you're thinking shortest distance. Shortest distance means minimum. Okay? So we are using our distance formula. What's the distance? I'll call that D. All right? Can we remember what the distance formula is?
Yeah.
S
Square root 0 plus VT.
I thought it was
Y.
Not physics
Square.
distance.
One
Square
minus
root of x2 minus x1 parentheses squared plus, and then the same thing with y.
What is
What?
this?
x2 minus x.
What is this?
That's our distance formula, okay? Now guys, here's the thing.
So how do you
Here's the thing. Don't get caught up in the formula. You guys know how to find the distance between these 2 points.
Oh yeah.
I'm trying to find that distance D so I can make a little right triangle, right?
Yeah.
If you can't remember the formula, that's okay. How long is this side right here? Well, if this is at x and this is at 0, I know that this side right here has to be x. X minus 0. That's the x2 minus x1. All right? So I know, first of all, that this is just going to be x squared. Okay? And then notice here, let's zoom back in. If this is up here at 4 minus x squared and this is at 2, then the distance between them is going to be 4 minus x squared minus 2. You guys know how to find distances like that. Well, hey, that's our y2 minus y1 in the formula. All right, so this is just going to be 2 minus x squared. So that is what we're squaring there. Okay? So don't get caught up in a formula. Think. You guys can find distances between things using the Pythagorean theorem. Okay? Now, in this case, it may be helpful to go ahead and FOIL what's inside there. Okay? So let's go ahead and do that and simplify some, and then we'll take our derivative. Okay? So, square root of x squared plus 4 minus 4x squared plus x to the 4th. So we have x to the 4th minus 3x squared plus 4. Okay? That's the function itself. We're trying to find the shortest possible distance.
Yes.
Okay? So I'm finding the distance between 0, 2 and any point on the graph. I could have drawn it down to here and said, hey, that's point P. It's some x and the y is 4 minus x squared.
I know that.
Okay? I just picked a point that looked a little bit closer. Okay? So now to find the min, we're going to take the derivative. Okay? Let's go ahead and take the derivative. So d prime is going to be what?
1/2 times x to the 4th minus 3x squared plus 4 on all of that to the negative 1/2 power multiplied by 4x to the 3rd minus 6x. Sorry, times net. Wait a minute. Yeah, minus 6x.
You guys agree with that?
Oh, he's so clever. I didn't get this.
Yeah, that's great. That's good. Now we get it. Okay? So now let's simplify this a little bit. Because at this point I need to find the min point. Alright?
Would you do 4x to the 3rd minus 6x all over 2x to the 4th minus 6x squared plus 8, all that to 1/2 power?
Well, you can't distribute the 1/2 in because it's to the 1/2 power. I can distribute the 1/2 into here
Oh.
and make that a 2x cubed minus 3x. And then my denominator is going to be the square root of x to the 4th minus 3x squared plus 4. Okay? Now, we've got some critical points. Okay? We've got some critical points here. We actually have quite a few critical points. Because critical points can come when the derivative is 0 or when the derivative is undefined, right?
Yeah.
So, let's think this through. D prime equals 0 when what happens? 2x cubed minus 3x equals 0, alright? When the numerator is 0. So let's solve that. We have x times 2x squared minus 3. So what would x equal?
0 and square root of positive we have, and negative we have.
Good. Negative or positive square root of 3/2. Okay? Which you could make square root of 6 over 2.
Wait, is it the whole thing square root or just the square root?
The whole thing is square rooted, because you'd add 3, then divide by 2, then square root. Okay? So then we have, where is d prime is undefined?
The bottom is equals to 0.
When the bottom equals 0, yeah. Okay, so square root equals 0 when what's inside equals 0. So x to the 4th minus 3x squared plus 4 has to equal 0. Okay?
Do we solve this equation?
How do we solve it? Maybe you could try synthetic division. But this is a quadratic form, right? Even though it's x to the 4th, the middle term is x squared, the last term is constant. So we can use a quadratic form, but in this case, the x squared would equal negative b plus or minus square root of b squared minus 4ac all over 2a. Okay? So I would need to, now what would I find first of all? What do you always calculate first when you're doing the quadratic formula?
Like the square root inside.
Yeah, what's in the square root? Because if it's negative in this case, we can stop and we're done. So let's go ahead and do that. B squared would be 9 minus 4 times 1 times 4, which is negative.
We are done.
So we're done.
Yeah.
So, nowhere.
It's like obvious, you shouldn't even have to do it.
Yeah.
Because.
So,
Oh no, it's not obvious. Oh no, it's not.
so there are no real values of x that will make this undefined.
Oh,
Okay.
Undefined, yeah.
Undefined.
Undefined is wait. Undefined is when the derivative does not exist, right? Or is it when it's zero?
Undefined is when the derivative is not, is when the derivative does not exist, yeah, because
It's a problem.
something over 0.
In that
okay.
round space.
Now, this one, x to the 4th here, it's never equal to 0. We know and we know this is increasing as we go to the right because it's a positive x to the 4th. So I'm not sure exactly what's going on with this, but this is something you'd have to be careful with because it's possible that since it's in a square root, it could be negative, right? But in this case, I know it's never going to be negative because if it never equals 0, but the y-intercept is up here at 4, then I know it must look something like this, right? Just based off of what we know. So no matter what I square root, it's going to be the square root of a positive number. So again, I know that that d is never going to be undefined. All right, so now I'm left with just these critical numbers, and I can set up a sign diagram to help me find where my min will be. Okay? So I have 0, I have positive square root of 3/2, and I have negative square root of 3/2. Okay? So let's try some different values in here. What's a number between 0 and the square root of 3/2?
Square root of 1.
1. Yeah, square root of 1.5 is going to be bigger than 1. So let's try 1 in our derivative. Okay? If I plug in a 1 in our derivative, I have 2 minus 3 is negative. The denominator is going to be the square root, and we already said the denominator is always going to be positive. So it's going to be a negative number. All right, so I know that my derivative is negative here.
Wait a minute.
And then
X to the 4th would be 1, and then 3x squared would also be 1. So 1, oh, never mind, my bad.
It's
Scratch
okay.
that.
Plus 4.
That's okay, we're thinking it through. All right, so now let's try something to the right of square root of 3/2.
real quick, why are you doing this if you already graphed the function, you already know it's increasing and then decreasing?
I don't know, that was just the denominator. That was just the denominator down there.
Oh,
Okay? I was just showing that the denominator is never going to be negative, so I don't need to worry about where the square root would be imaginary.
know what I'm saying, the drawing that you did.
Well, the drawing, notice, that is not the distance. That's not the graph of the function that I'm trying to minimize.
Oh,
This is the function I'm trying to minimize. I don't know what that looks like.
oh,
Okay? So that's why we're having to do this sign diagram. Alright, so here we have a negative between 0 and 3/2. Let's plug in 2. Okay, because I know square root of 3/2 is less than square root of 4, so let's plug in 2. I'm going to get 2 times 8 is 16 minus 6. That's going to be positive in the numerator, and I know the denominator is positive. So now I know over here it's positive. Okay? If I try over here on the left side of 0, if I plug in a negative 1, I'm going to get a negative 2 plus 3 in the numerator. That's positive. So this whole range is going to be positive. Okay? And then if I plug in a negative 2, I'm going to have negative 16 plus 6, which is a negative 10. So that's going to be negative here. Okay? So, where are the min points?
Negative root 3 over 2.
Negative root 3 over 2 is a min,
And root 3 over 2.
and root 3 over 2 is a min. Okay? So, I should actually find what those points are. So it'd be negative square root of 3 halves something, and positive square root of 3 halves something. So I'd go back, plug it into my distance formula, and I'd have 3 halves plus 2 minus 3 halves squared. 2 minus 3 halves, 2 minus 3 halves would be a half, squared is a quarter. So I'm taking the square root of 3 halves plus a quarter. So the square root of 1.5 plus a quarter would be 1 3/4. So that's 7/4. Or radical 7 over 2. Now I know those are both going to be identical because in my function I was squaring the x's, so it doesn't matter if I was plugging in a negative or a positive root 3 over 2, I'd get the same thing. Yes?
If you're plugging it back into the like distance, why aren't you plugging it back into the y equals 4 minus x squared?
Y equals 4 minus x squared.
Because you're looking at which points are that on that graph is the distance.
Oh, wait. No, you're right. Which points on the graph? These are, that gives me the distance. No, good catch. D, our distance minimum is going to be the square root of 7 over 2. Thank you. The points are going to be from, you're right, the original graph. So 4 minus 3 halves, 4 minus 1.5 is going to be 2.5. Okay? And that's going to be the same for both of them because I'm squaring the x. Okay? So, which points? These are the points on the graph. If you want to know the distance is square root of 7 over 2. But thank you for catching that. Davi?
Mr. Hicks, I'm having trouble when understanding why you're calculating the derivative of distance in the first place, since it's going to give you this slope. I don't understand why you need this slope.
Why did we plug what in?
Why did you solve the derivative of the distance?
Well, because we wanted to find the max or the min of the distance. And the max or the min of the distance is going to happen when the slope of the tangent line is 0.
But aren't you then finding the max and minimum slope?
No. The max or min of a function is when the rate of change is 0. When the slope is 0. So you're finding the max. We found the maximum distance is going to be when x is 0. The minimum distance is going to be when x is plus or minus square root of 3 halves.